Today we're going to learn about compound inequalities. With compound inequalities, it's two inequalities that are combined to create one statement. And in many real-life situations, you're having to deal with different levels and different ranges where you're going to have to combine them to get the reasonable answer based off of the situation. And for compound inequalities, you're dealing with two different types. One are your and statements, and the other are or statements. And again, as we work through these, you'll see the difference between and or. Remembering, compound inequalities are a combination of two inequalities to create one statement. So let's talk about and statements for a second. I'm going to give you two separate ones. We've got x is greater than -3 and x is less than or equal to 4. Because it's an and statement, I've got to look to make sure to graph it, and I'm going to look to see where these two inequalities overlap or share in their shading. So I go to my number line, I graph each of them separately. X being greater than -3. I see the shading going to the right, and I see x must be less than or equal to 4. Remember, it's a closed circle, and I see it's less than or equal to 4. So when I'm working through, I got to see where these overlap. Noticing this one is going to the right with an open circle, and this one going to the left. And I see that they share this shaded region. So as I write and statement in this situation, as I combine these two, it's going to be -3 less than x, which is less than or equal to 4. This type of statement right here is called a between statement. Because again, my x value must be between -3 and 4. So you'll see represented inequalities and statements represented like this, two separate ones separated by and, or you're going to find them represented as one compound inequality, again recognizing it's a between statement. The difference between and statements and or statements is that with and, you must look at the shared shaded region, or the values of x that satisfy both. Again, the values of x that satisfy both inequalities, or it can be one or the other, so it doesn't have to satisfy both. So we'll give you guys an example. We have x is less than or equal to 0, or x is greater than 5. So I put that on my number line, and I've got x being less than or equal to 0, again going that way, and x must be greater than or equal to 5, open circle because it's not inclusive, going to the right. Notice that there is no overlap here. It does not matter because, again, it can be one or the other. And statements, it must satisfy both. So a couple situations you're going to look at is one going from the inequality, representing it on a graph, and then vice versa. So let's look at one example of an and statement that you'll look at, and we need to write the appropriate inequality. So if we look at this, we have a number line, and we've got a value of -3 and closed circle, and then a value of 8. We have an open circle, and I notice that the shading, again, is between -3 and 8. So I can represent that two ways. -3 is less than or equal to x, which is less than 8. I could also represent it as two separate ones combined with and. X must be greater than or equal to -3, which takes care of this piece, greater than or equal to -3. And X must be less than 8. So again, being able to go both directions is really crucial as we get started with compound inequalities. Or statements, you're going to look at something like this. -4, closed circle, shading going to the left. We've got +2, closed circle as well, shading going to the right. I notice if this is given to me, it cannot be an and statement because this is the inequality. And because they're going in different directions, I got to recognize that it is an or statement. So I'm going to write this, and I can't combine or statements into and statements that look like this. All or statements will be separated by the word or. So I get X must be less than or equal to -4, or X must be greater than 2. I cannot combine these. They have to be left separate because, again, there is no overlap. All right, let's implement some solving of inequalities, a little bit of what we did from 6.1 into these types of statements. All right, so I'm going to look at a problem. So let's start it off. Let's go with 5 is less than or equal to 5x plus 2, which is less than or equal to 8. Noticing it's one full between statement, I'm going to recognize that this is an and statement. I'm going to look to break this off. There are a couple ways I can approach this. I can separate into two, or I can apply by solving through the entire piece. So remember, if I subtract 2, treating it just like your basic inequalities, I have to address every single piece of that inequality. So I subtract 2 from the middle. I must subtract 2 from the outsides as well, every single piece. So again, I'm left with 3 is less than or equal to 5x, which is less than or equal to 6. Remember, I've got to get x by itself, so I need to divide every single piece by 5. And what I'm left with is 3/5 is less than or equal to x, which is less than or equal to 6/5. Even though I have fractions, that's okay. Once I get to this point, when we're working with solving, we're going to always ask you to graph that inequality. So at the end, I need to get to my number line. Again, I've got 3/5, and I've got 6/5, and I need to label the graph appropriately. So what I do is, again, I know x has got to be greater than or equal to, so it's a closed circle going that way, and less than or equal to 6/5. And it's the shading that is overlapping. So again, remember, this is a between statement, which is also an and statement. Okay, now, this is an example of solving a compound inequality and statement. So let's do an example of solving a compound inequality or statement. So we're going to take two examples. We've got 3x is less than or equal to 12, or let's think about this one. So that's so let's go x must be, let's go greater than or equal to, let's go 5x must be greater than or equal to 35. Okay, so I'm going to treat them just the same as solving one inequality, but I'm going to treat them separately. So I address this piece first. So I divide by 3, and I get x is less than or equal to 4. Or, make sure I always bring that down so when I graph I remember it's an or statement. I divide by 5 for the second piece, and I get x is less than or equal to 7. I'm sorry, greater than or equal to 7. So after I solve each piece, I'm going to graph these on my number line. So I know 4 less than or equal to, and x must be greater than or equal to 7. Knowing the difference between the two is crucial. Let's do another example and see where some of the kind of special cases come up. Alright, now, if I'm giving you guys a problem like this, and we're going to like for you guys to graph, that if you get to a solution and say x must be greater than -4 and x must be less than -7. Let's go ahead and graph these. So I know -7 is below -4, so -7. X must be less than -7, and x must be greater than -4. Now look at that. In an AND statement, it has to satisfy both. So again, I'm looking for overlapping, where they share. And notice as I graph that they have no shared shaded region. So there is no value for x that's going to satisfy both. So there's actually no number that it works for. So for this situation, this is again a special case for the AND statement, that if you get to those final inequalities and graph them, and you recognize that they do not intersect, there is no solution to this problem. And we use this sign, which is null set, to represent this. So again, a special case. Please make note of that, because you're going to find those coming up. All right, now let's look at a special case for OR statements. So let's look at x being greater than or equal to -2, or x being less than or equal to 5. So I go ahead and graph. I get -2, closed circle, going that way. And I've got 5, closed circle, going this way. Now, as I look at this, it can be that or that. So I'm looking for all of the pieces that x can be. And if I notice that the shading carries through every single number, that x can be anything on the number line. So again, how do we represent something where x can be all the numbers? So in this situation, your answer is all real numbers. That's the special case for OR. Null set, the special case for ANDs. But again, making sure you pay attention to all the little ways as far as solving inequalities that you guys worked on in 6.1. But we'll do some more advanced problems as we're going, along with word problems to expand on our critical thinking. But again, understanding compound inequalities, combining two inequalities into one statement. Good luck.